Right, in this quick video, we're going to have a look at how you approach some more difficult, more complicated problems. The first bits of advice we can give you, just generically for any problem, is firstly, make sure you understand the question. Do you know what it is actually asking you to find? Do you understand all of the terms in it? Do you understand the situation that's being described? If you don't, there's no point going any further than this. You need to understand all of those things. Once you're happy you understand what it says and what it's being asking you for, you need to gather all your information together. So, best in the form of a diagram, write on any bits of information the question has given you. Also look for hidden bits of information. For example, if a ball is dropped, you know the start velocity would be 0. You have to know the equations, laws, and principles being used. You've basically got to have studied the relevant chapters before you can answer a question. If you're not aware of what equations are available to you, you're not going to be able to solve the problem. But you do also need to be aware of the principles you're going to apply. Otherwise, there could be something that you've missed or a way through the problem that you won't otherwise see. The final thing is to start somewhere. The biggest problem that students have with complicated problems is that they don't start. And until you take that first step, you can't take a second, and that eventually leads to the end. A lot of students won't start something until they can see what the answer is. In complicated problem solving, you're not going to know what the answer is until you get to it about halfway through or even later your workings. You've got to start somewhere, even if it's a dead end. Otherwise, you're never going to get to an answer. Let's take a look at this little example. So a ball on a string, 0.8 meters, swung in a vertical circle. It travels at the minimum velocity possible to keep the string straight. The tension in the string drops to nothing at the highest point. Find the velocity at the highest point. Okay, so not too complicated a situation, but it's not perhaps as straightforward as it first seems. What we need to do is get the situation in our head. So we need to start with a diagram. This is always a must. There are very few questions that you don't start with a diagram for. So we've got a ball being swung in a vertical circle, so I need a quick sketch of a vertical circle. Attached at the centre, I'll draw the ball maybe in a couple of positions around this. And what other information do we know? This distance, I'm going to call it r because it's the radius of a circle, but I might be prepared to change that later, is 0.8 meters. It travels at the minimum velocity possible to keep the string straight. Be careful of making any assumptions about that. We'll get to that in just a second. What that tells us is something about the circular motion situation. The tension in the string drops to nothing at the highest point. So up here, T is 0. Down here, T is, I'm just going to call it T max. The only reason I'm putting that in is so I don't assume later on that the tension is 0 all the way round. That tells me that it changes. I also need to be clear about what it is I've been asked to find. I've been asked to find the velocity at the highest point. I'm going to assume it's going that way for no other reason than it's convenient. So that's all we need. There could be more information on this. There might be things like gravity being 9.81, all sorts of stuff that might be involved. We don't know the mass of the ball or anything else. We probably don't need to. Okay, next thing is, do we understand the question? I need the velocity, and do I understand the situation? Now, yes, it's a ball on a string being swung around, but that doesn't mean I understand the situation. What does everything in the question actually mean? Why is it there? I've got a distance. Okay, that's easy. Swung on a vertical circle. Well, that's quite important, actually. Do I understand what that means? The ball might not be travelling at a constant velocity. In fact, as it comes up the side here, it's going to get slower. So the velocity isn't going to be constant. The velocity at the top would be lowest. The velocity at the bottom would be highest. Okay, so I understand what the vertical circle part means. It travels at the minimum velocity possible to keep the string straight, but the tension in the string drops to nothing at the highest point. Right, what does that mean? If a ball on a string is flying around in a circle, if it's going too slowly, that might be the circular path it would take, and the actual path of the ball might be something like that, and it falls out of the circular path. It needs to go at a certain speed to maintain the circular route round. Right, so that tells me something about what the ball needs to have or be at the top. So the principles I'm applying here, probably something to do with gravity. So equations might be weight equals mg, for instance. Something to do with circular motion. So what I want to do is write down a few circular motion equations. But also think about the principles. It's not just about circular motion. So some things that might help me are omega is the angular frequencies, v over r. It's also 2 pi f. I know this isn't the proper way of writing equations, but this is just back of the envelope stuff for me, really. If I know it's 2 pi f, I also know it's 2 pi over t. I know centripetal acceleration is v squared over r. And therefore I know centripetal force is mv squared over r. Possibly F equals MA might be useful. If I'm completely lost, the more things I can write down, the better. You might think, well, this is getting really confusing. I'm not going to use all these things, but if they're there, I might be able to see them. I've got a circle, so the circumference of a circle is 2 pi r. I've got a radius, so that could be handy. It's possible this is an energy problem as well. So, you know, an object that moves up and down, it's got kinetic energy. I could have the kinetic energy as half mv squared, potential energy is mgh. That could come in quite handy. There's a few other circular motion equations as well I might want to be aware of, other versions of A and F, and you could add as many of those as you can think of to the list. Okay, so let's try a few methods. I think I'm clear about the information. Maybe there's just one more thing that's bugging me, is this tension drops to 0 at the highest point. Now, if I don't know what that means, I could launch into the question, but this is clearly important. What does that mean? Okay, so when an object's moving in a circle, it needs a centripetal force or a centripetal acceleration. Now, that will be provided by the tension in the string. If the tension in the string at the top is 0, what does that mean? It's still travelling in a circle when it goes past this point. What's providing the centripetal acceleration or centripetal force? If it's not the tension in the string, the only other thing could be the weight. Ah, right. So at this point, right at the top, the centripetal force or acceleration is equal to or due to gravity. Realising little things about the question and what's going on in the situation makes life a lot easier when you come to actually sort it out for yourself. Okay, so now we're ready to have a little go. Method 1 might be, well, we'll just guess. Maybe it's a nice, easy question. You know what? Sometimes it is true. Is the velocity at the top 0? Okay, well, check the answer makes sense. No, it really doesn't. If the velocity at the top was 0, the ball would just drop straight down. It wouldn't carry on moving in a circle, so it isn't something easy like that. But you know what? It's always worth checking. We do sometimes ask you really straightforward questions. Method 2, I'm really not sure what to do, so I'm going to pick an equation and try something. All right, let's try v equals distance over time. And I know the distance is the circumference, so v equals 2 pi r over t. Okay, that gives me one circle. I don't have the time, but that's not a reason not to carry on down this path. I do have r, and it does give me v, except that v is going to be the average velocity, and it's not going to be the velocity at the top. I could potentially work something out from that if I knew another velocity, but at this point I don't, so maybe this is a bit of a dead end. Okay, method 3, let's apply a little bit of the physics principles and think about it. We had that thought that the centripetal force at the top is equal to the weight, or the centripetal acceleration is going to be equal to gravity. Right, so centripetal acceleration, this is at the top of the circle, is going to be equal to g, 9.81. Right, what does that tell us? Let's try something. I've got these equations. A equals v squared over r. And if a, the acceleration, is equal to g, then I can say that g equals v squared over r. All right, let's just check and see what I've got. G, obviously I know, it's 9.81. R, that's a distance. Okay, I've got that too. And the velocity, this isn't the average velocity, this is going to be the velocity at the top. That's what I actually want. If I rearrange this, I'd have that, and I know both of the things in it. So this is not such a horrible question after all, but it does give us an idea of the way we might need to start looking at these kinds of problems. This gets a bit more complicated if we had multiple layers. So for example, if this worked, but I didn't know one of these things, I might then need to bring another equation in to work that out. From here, I can just substitute the numbers in, and the rest is relatively easy.